good afternoon. Welcome to our extraordinary seminar. It's extraordinary not because it's on Tuesday and not just because it's Kevin Knight, but because it's after the semester. Anyway, we are privileged to have Kevin Knight, who flew in just for this occasion from Southern California. I mean, it's not a big deal to fly in when there is spring here. So actually, okay, anyway, he's from the Information Science Institute, got his PhD from Carnegie Mellon, is, I guess, an owner of Language Weaver. Is this correct?
Co-founder.
Co-founder of Language Weaver and a famous personality in machine translation.
Okay, that's quite an introduction. Thank you. So I want to thank everybody here for inviting me. It's nice to be here. I haven't been here for 8 years, I think. So walking around here is really reminding me of the summer workshop we did here a while back. So this is the title of my talk. It's kind of a long title. Machine translation equals automata theory plus probability theory plus linguistics, or can a machine translate without knowing what a verb is? And I think this will work better if it's interactive, so please just interrupt me with questions starting right away. Okay, this is joint work with Daniel Marco, Wei Wang, students and collaborators at ISI, also summer visitors who've come to work with us, Dan Hua from UPenn, Hassan from Rochester, Michelle Galley, and Mark Hopkins from Columbia and UCLA. Okay, you guys all know this story, so I think I can skip this slide. This is a good problem. Your family can understand what you do when you explain it to them, and they ask you, hasn't this already been solved? And you say no, and okay, it's easy to explain. And statistical MT, I think you guys already got this picture too. The human translated documents get fed in the machine. The machine learns things, and this is driven by, well, by a lot of things, but it's driven a lot by the amount of bilingual material that's online. So for Chinese English and Arabic English, there's plenty. And it's still growing. And for a lot of language pairs, you can get millions or hundreds of millions of words of parallel material, and for many, many language pairs, you can get millions of words of parallel training material to feed to the machine. Okay, so what do we do with the bilingual text? Let's say we have 200 million words. This is what we have been typically doing over the past few years. We word align it, so try to figure out which words correspond to which other words. This is an errorful process, but it's adequate. And then from these word connections, we can find phrases, like this one is a translation of that one, and pull out a vast database of phrase pairs, some of which we observe many times and some of which we observe maybe just once. Okay, so this is a nice algorithm from Franzo. And then we can use these phrase pairs to translate new sentences. So there's a new sentence, if I can work this. Chinese sentence at the top, never been seen before in the training data. And these are all the phrases, not all the phrases, but a lot of the phrases that the system gets in order to translate that new sentence. So you can see that first word, the system thinks, well, from its experience might be translated as the, it, this, these, or that. This one, these two words could translate as a phrase to the astronauts, or astronaut, cosmonauts, or international astronomical of rapporteur. So there's some very strange translations in here. These are all learned from the data. Okay, and what we want to do is now pull rectangles off of this chart in order to assemble a good translation. And there are many ways to do that. Here's one. We could say, these 7 people include, and then we might go over here and say, these 7 people include astronauts, translating that whole phrase instead of space members or something like that. And then we can keep going around pulling more rectangles off the chart, and the goal is to pull them off in such a way that we account for every Chinese word exactly once. So these 7 people include astronauts coming from France and Russia, period. That'd be a good translation. And of course, there's billions of ways to pull off rectangles from this chart and order them. So we want to score all the different ways. And 2 scoring methods that are common are, well, try to use phrase pairs that have been frequently observed instead of infrequently observed. So maybe astronauts is a more frequent translation of this than astronavigation member. So that's one thing, use frequent phrase pairs. And the other thing is try to output a sentence that has good English word sequences. So these 7 people include instead of these, well, 7 people, these include the worst English. Okay, so, and if you want to think about those 2 knowledge sources, I guess think about them in this way. Some people it's very intuitive, and others it's not. But you can think about a language model producing strings according to distribution, and translation model turning those English strings into Chinese strings. And these are tables relating pairs of strings and relating scoring strings. These tables get shoved into the decoder as the knowledge to translate now a Chinese string into an English string, and never seen before a Chinese string into an English string. Okay, and you can think about that as a weighted finite state acceptor if you want to. And this is a weighted finite state transducer if you want to, and this is some kind of finite state composition and best path search. Okay, so then we have these 2 knowledge sources that we like, the trigram model and the phrase pair frequency, or maybe conditional probability. You can do it different ways, and you can weight those and say, I believe this one more than that one. And then people use a bunch of other ones. There's a bad phrase spotter usually in these systems, so word drop spotter, move me preference. Some phrases like to be moved, and other ones like to stay where they are, and output length, so that you can adjust this to make longer or shorter outputs. We want to get an output that's about the right length. Okay, and if you fiddle with these, then you can affect the translation quality wildly. So here's an example of the space. Here the translation model, conditional probability of the phrase pairs have been picked at 1. And here we're able to modify the weight we assign to the n-gram language model and the weight we assign to the length of the output. And you can see, so as we manipulate these 2 weights with that one fixed at 1.0, we get the translation quality, which is here in this vertical axis, varies a lot. So if you just set the weights randomly, you'll be down here and get a very bad translator. Maybe this one outputs things that are way too short, or maybe just uses the wrong words, or it's very English-like but doesn't translate well. And so what you want to do is get up here with these weight settings to make sure the translations are as good as you can be. And Franzo contributed a very nice algorithm to the field, which is the maximum blue training, or sometimes called MERT, to get you from wherever you happen to start randomly, like here, up to there where you get a better translator. Okay, so that's it for kind of summary of phrase-based machine translation. So the phrase-based progress has been good based on those ideas. So these are all phrase-based systems from 2002 to 2005 on the NIST Common Evaluation Arabic sets. Okay. Okay, so can a machine translate without knowing what a verb is? Of course. But the output's often bad. So here's a typical sentence. Foreign high-tech exports are bright spots for foreign trade growth of Guangdong has made important contributions. And you can see how this gets created by that method. We just pull these rectangles off the chart and we try to stick them together so that the English subsequences are good. It's just very frequent that you get this kind of output. And so this kind of story about pulling these rectangles off the chart, it's a reasonable first approximation, but it breaks down almost all the time for Chinese to English translation, for example. And so it needs to be improved. So that's where we get to syntax. So if you look at that sentence, not very good syntax, and we'd like to be able to improve that. So maybe we need some grammar. So the way we're going to introduce grammar here is a very simple idea. So the phrase-based output takes a new Chinese sentence, this is another one, and outputs a string. And maybe this is decoder hypothesis number 1, and it gets assigned some score. Gunman of police killed. And it looks for other translations, like gunman of police attack, gunman by police killed, killed, gunman by police, gunman killed the police, gunman killed by police. And in our decoder, this is the highest scoring output, given all those knowledge sources that have been properly related. Okay, does that make sense? All right, so there's a bunch of problems here. So this is not a headline, this is a sentence in the middle of an article. So the past tense verb needs a direct object. There's no direct object for kill, but if it's a past participle, then it's missing the was or the were. Gunman it needs an article, a or the. This word right here in Chinese is a passive marker. So what it's really doing is controlling how you might reorder things. It's not it doesn't need to be translated literally. So what we want to do is inform the machine translation system of all this stuff, and then it'll be better. But the problem is you can't tell it what all these things are because it doesn't know what a verb is, doesn't know what a past participle is. So it's really hard to just stick this information into the system. So the syntax story is almost exactly the same, except that we take a Chinese sentence as input and we output trees in the decoder. So this is decoder hypothesis number one, the gunman killed 5 police. And we not only get that string, but we get this whole structure. So the decoder's job is to turn that Chinese string into this candidate English tree. And it scores that one. Gunman by police shot. Scores that one. And the gunman was killed by police. This is the highest scoring output from the syntax model. So now it is. So we spent probably a whole year trying to get that sentence just to come out of the decoder. So happy when it happened. Had a little celebration with cake and everything. Okay.
You should have a picture of that on the slide.
Yeah.
The celebration. The celebration.
Yeah, you just have to imagine in your head. Probably you imagine it better than it really was. So, this is okay so far? Interrupt me with any questions. Okay, so the idea is that maybe we can get better modeling of target language structure because maybe we can always have a verb, and maybe the verb will be in the right place, that there's better handling of function words, like that passive marker. Don't translate them, let them control the translation, and maybe better generalizations in the translation patterns. We don't have to memorize, specific road phrases, but it can generalize them. Okay. So this is the idea that we've been working along for quite a while, actually. So we're a bunch of people at a bunch of places working on syntax-based approaches to translation. This is where a system knows what a noun is, what a verb is, prepositional phrases, and so on. And at least in my hallway, down to the left, there's language engineers who say syntax will never work. Syntax has been shown to make things worse in machine translation, and there is the citation to prove it. So we had to deal with this. And then on the right, and down the other hallway, is the AI fellows. We have a bunch of these also at ISI. Syntax will never work because you need semantics. And that's the only way it's going to work. So we're very unhappy for a long time because we were surely doing the wrong thing. And sure enough, all those people were actually right. Because in the phrase-based, this is just a copy of that phrase-based machine translation progress chart I showed you. So 2002, 2003, 2004, 2005, phrase-based system made very good progress. And basically, there was a syntax system here, for example, built by us, that didn't work. There's another one built there, didn't work, that one didn't work, this one didn't work. So year to year, we have to say it didn't work. Okay, so last year was a good year for us because it started to work. So here's our story from last year. So let's see. Okay, so here were short sentences of less than 16 words, and more longer sentences that we couldn't translate with this method. The computation is just too difficult. And worse than that, okay, it's a couple of years ago, here's the phrase-based system on these short sentences also. So this is the system we're trying to beat. And very bad performance for a long, long time. And then finally we are able to get the decoder working, and I'll talk to some about how it works later in the talk. And then so happy we beat the phrase-based system here. And from this point we feel good because once the system knows what a noun and a verb is, it's you feel like now you see an open path in front of you because, well, now you can tell it all those things. Don't do that with the verb, and don't do this with a noun, and you need a direct object for a transitive verb, and you could have all kinds of things going on to improve the system, and sure enough, we could improve the system. So again, very happy. Then we said, okay, let's translate all the sentences in some standard test set. Very sad again. Okay, so here's the phrase-based baseline. It's harder to translate long sentences than short sentences, but here we are with a system we really liked. It was a complete failure trying to translate long sentences. So, okay, blah, blah. Continue, and now it seems like actually getting better. Okay, so I want to talk about what are the sort of key ideas.
So I don't understand, you've got dotted lines there.
That's because this goes from July to January. So I didn't know how to
So there
indicate
actually is a
that.
connection.
I didn't want the slope to be
That point on the right is an actual point.
Yeah, so it should be over here.
It's just the slope is not an actual
So
slope.
the line should have had a little break in it to show that.
Okay. Make sense? All right. Okay, and these are just some numbers that will have a more or less this one thing. oh, no, I should say here. So things work out very good for Chinese English. So phrase-based system is here. This is our phrase-based system. Now this thing's been sort of, and then syntax-based system here. So good improvement. But when we look at Arabic, the improvement is very small, or small anyway. So this sort of approach is working well here, but not working well here, and there's various reasons that might be the case. And we can speculate. But we've also been doing a lot of, most of our work is focused, I guess, on this language pair. And now we're putting some focus on this one. But also Chinese has a lot more reordering of prepositional phrases and such than Arabic has. And the English that comes out of phrase-based systems in Chinese is very garbled English. So there's a lot to improve on. So, and this is a higher score, so there's less to improve on. So there's some ideas about why maybe we're not getting a bigger benefit here. So there's a lot more work to do, that's fine. Okay, so here's an example translation. It's kind of small, so I'll read it. The Chinese input here, and the phrase-based system says investment in Macau has become the largest foreign investors. And the output from the syntax system is this whole tree, not just the string. So the Chinese funded enterprises have become the largest external investor in Macau. And so, with the phrase-based system, it does have a verb here, but often there is no verb. With the syntax system, there's the verb, and it's right there, right in the middle of the sentence. If it wasn't here, we wouldn't have been able to make the S, and the decoder wouldn't have output it. That's it.
So it doesn't have a plural.
Right. This is, right. It should have the investors here. That's right. So it doesn't have enough of neither the translation model nor the language model knows about that. But that's a kind of great thing because there's all this opportunity now to say if you had a subject of a become, then the plural, then the object might be of the become might also match the gender. We can start to instruct the system with features that said that kind of stuff. Now, when you look at real data, none of those features work as easily as you think they might in your head. There's another sentence we have. Let's see, Canada and China should be a good partner. And should be good partners. So there's lots to do here. And here's an example of a more egregious mistake. Ding Hao was subsequently entered junior high school. So was subsequently entered junior high school. That's not good. So you could say he subsequently entered junior high school. Or you could say junior high school was subsequently entered by Ding Hao. But you can't have the passive together with the direct object, and the system just doesn't know that. So it thinks that this is a VP, that's VP, and all these things have been glued together to make an S, and everything's fine, it's happy, it got to the S. But it doesn't know that in English you can't have direct objects with passive verbs. Well, yeah, John was given an apple, maybe only with that transitive verb. So there's a lot of linguistics that the system doesn't know about, but given that kind of structure, you feel like you can start to tell the system more of that sort of thing. Okay, so then back to the kind of key idea. So when I'm looking back, I'm thinking, okay, so why are things getting better? Probably the right answer is engineering. So when you're in the daily, trying to make the system better, it's 95, 99% of your time goes into that. And you just got to get it to work and get the bugs out. So that's the truth. And so if I put up this slide aside, everyone will laugh. But when I think sort of besides that, what has to happen or what happened for us was, I think we found a clean representation for the syntactic translation model. That was really important. So all those years of, okay, it didn't work. This is I think the biggest event for us to make it start to be a good working system. And we got that from tree automata theory that I'll talk about in the rest of the talk. Also linguistic extraction methods, so we need methods to populate a syntactic model from data. And there you can see some references. Also to optimize the syntax. There's nothing that says the syntax of the Penn tree bank is optimized for translation, so there's things to do there, that was important. And then faster algorithms, so to enable the decoding of long sentences and enable automatic max blue tuning on long sentences. So that was another big deal. And so these are kind of the areas where in the top line what we had to do is find a model. We found a model from automata theory that matched the linguistic facts pretty well. And so that was a marriage of these two things to get that to work. And then we have to extract out linguistically plausible rules with good probabilities, and then we need faster algorithms. So I'll sort of describe other things things that have gone on in these areas that are kind of some of the key ideas. Okay, so The basic story is again a noise channel model. So this is the same thing I showed before. Some language model generates English strings. Some translation model corrupts those strings into Chinese, and then we have to decorrupt them going backwards. And that, well, the only change we're going to make here is remove the word string there and replace it with the word tree. And this will account for all the type of reasoning that I talked about before. So, but when we do that, okay, so now we got to figure out what these models are, and then we also have to figure out how to decode so that we produce not a string decorruption, but a tree decorruption. So that's 3 new problems to think about, and this is the one that I want to talk about next. So how does the English tree become a Chinese string? So I have this 42 volume set on my wall about how an English tree becomes a Chinese string. It's full of rules, 142 million rules from the system. And when you open it up, what does it look like? Well, it could look like all kinds of things. You have a lot of freedom to choose this kind of model, but that's the kind of scientific problem. How does an English tree become a Chinese string to where it means the same thing? So our first cut was a model that looked like this. We thought, hey, an English tree might look like this. There might be some probabilistic steps that reorder it. So we reorder this noun, verb, verb into, we swap these 2 things. So we put the main verb at the end. You change to music in Japanese, it would be music to. Okay, so we have some reordering. And then we have some word insertion, in this case, some Japanese particles. And then we translate whatever words are still in English into Japanese one by one. So, and then we get this tree, and then we throw away all the internal nodes, and we get this Japanese string. So that's the story of how an English tree becomes a Japanese string. And it's a probabilistic story, so we can hack up a lot of C code for that story. And some of the C code does the training and the rule extraction and probability estimation, decoding. Okay, so and then all that work, and it turned out that's not really a very good model of translation. It doesn't really fit the translation data that well. So we thought about it, and then we realized that, well, this is when we got turned on to tree automata theory, and this is much better. So here's the original paper was by Bill Rounds in 1970, also independently discovered by Thatcher in 1970. The idea is to take an input tree like this. He enjoys listening to music. Very faint green lines there, you have to imagine. And we have some automaton here that's going to take this input and turn it into Japanese. And it's not going to, it could be all kinds of things in this automata. But here's roughly what's going to happen. A rule's going to fire. Can't really get any good color here. All right. So a rule will fire and identify some initial substructure at the root. In this case,
there's like a yellow oval background around that section.
Yeah.
Okay.
So
Well, now that you pointed out, we can see it. I think.
Okay. I'll try to point out these invisible colors. All right. And then what's going to happen is it's going to take those nodes, those 5 nodes there, and apply some rule, and boom, it's going to, well, dismember the tree. So we got the he part, the listening to music part, and the enjoys part, and it reordered them. So I put the enjoys part at the end. And it also stuck in some actual, honest to goodness Japanese words in there. And now it has 5 items, some of which are trees, English trees, some of which are Japanese words. Tree, word, tree, word, tree. And now what it does is it just recursively works on the black English trees that are still left. It tries to turn them into red. So it might look at this guy here and say, okay, I'm going to turn that guy red. And then so on. Now it has to recursively work on this guy, so it'll pick some other rules or transitions, and eventually it gets all the Japanese. So now let's look inside the box. The way it really works is like a finite state transistor. So you start with this tree, start state Q. And so we needed a transition or a rule in here that has start state Q and that's looking at something compatible with this tree. Oh, I put a line around it. Okay, and so one rule that might fire on this particular tree here at the root, if you're in state Q and you see an S, it has 2 children, and the second child also has 2 children, and we can put some variables on these guys, x1, x0, x2, then it says, when you see this English fragment, translate it like this into Japanese. Or, this is just a tree transducer, it's just an automaton, it doesn't know it's English and Japanese. But if you see this, then output that, maybe with some probability. And a nice thing about these is, okay, whatever subtree is here, that's what's going to be recursively processed. And you could process that in a different state. It doesn't have to be state Q, it could be state S.
Kevin,
Yeah,
why don't you try this for me? That was really invisible right here.
thank you. Is that what you do?
Yeah.
Wow. Okay, so when we decide to reprocess recursively that noun phrase, we don't have to do it in state Q, like we were going to. We could transition to state S. And so when we apply that transition right there, and all the transitions in the automaton look like that. But then you get this. So now we have to recursively process this subtree, this one, and this one. We're going to do this one in state S. We're going to do this one in state R, and this one in state Q. So that's the top-down tree transducer. Here's another rule that might fire. If you're in state S and you see NP pro he, then you can translate that whole subtree into one tiny little Japanese word with some probability. You do that, and then to get the total probability of getting from there to there, it's more or less you multiply all the probabilities of the individual steps. So Bill Rounds didn't probabilize his machine, so we have to do that.
So this is the class XR, is that right? Or sorry, RX?
Yeah,
XR.
I'll get into,
Yeah, okay.
there's a lot of variations of this, and he invented something called R, which is now called T, for top-down tree transducer. They used to call it root to frontier transducer, because believe it or not, in these old books, they used to draw the trees like this, with the root at the bottom. Crazy. Okay, so they call it root to frontier and frontier to root, but now we call them top-down and bottom-up. Okay, so one nice thing is that this model we talked about before, you can just reprogram this thing as a single 4-state tree transducer. And so the tree transducers are very general, and they cover all sorts of things that you might want to do. If you want to do this, you can do it. It's not a good model, it turns out. But you could do all kinds of other better models, and that's what enabled us to think about these better models that can do much more stuff that previous model couldn't. So for example, translate a whole phrase is singing to its dot continuum. That's a good thing you might want to do in machine translation. Or non-constituent phrase, there are X translates to IX. And non-contiguous phrases, put X on, put near X. Context-sensitive word insertion. This multi-level reordering for English to Arabic, you want English is noun, verb, noun, and Arabic is verb, noun, noun, and so on. Okay, so and another nice thing about these transducers is, well, they look pretty expressive for machine translation, but they're also expressive for things people have proposed in question answering, compression, and paraphrasing. So between 2000 and 2004, there were a lot of papers with probabilistic tree-based models, and you could, almost all of those can be cast in this kind of transducer. Okay, so that was good that they're expressive, and now we can apply. Well, we could, if we can have machines that can deal with these kinds of things, maybe we could do better at the machine translation problem. So after we have that, then one thing that we learned was you could extract tree transducers from data. So if you have data like this, if you have an English tree and a Chinese string down there, and some word alignments here, it's hard to see, there's little lines there. Then we can automatically, from that data, pull out, for example, a rule like this. VBD felt translates to this Chinese word, or vice versa. This Chinese word translates to past tense felt. Now, noun felt would have a different translation into Chinese. Okay, and then what we're going to do here is circle these things such that no alignments come in or out of the oval, and that's the way the rule extractor works. So there's a linear time algorithm for this. And it can even learn things like, if you have a noun phrase and a verb phrase, and you want to translate the Chinese, just translate the noun phrase, translate the verb phrase, and glue them together. In another language, they might be reversed. Okay, so tree transducers can be extracted from data. Here's some, if you just grep through the file, if you see the said that X, how do you translate that into Chinese? So the system's opinion is shuo, comma, X is a good translation. Or just shuo X without the comma, without the Chinese comma, that's good. Or ta shuo X, this is not good because that means he said. But it's very low probability here. So there's still a lot of noise in the data, so we try to get good ones. Okay, here's NP from NP. System's idea is the best translation, or the most frequent translation of that into Chinese is flip the order of the two noun phrases and drop the word from. So that's kind of surprising, but that's what it found most of all. or you have the coming from x1 that modifies x0. So this is a modifier phrase for x0. Or the x1 possessive x0. Or this one's very good translation here. The coming from x1's possessive x0. That's kind of what I'd like to see. Okay, so any questions about that? How to get the rules?
Well, so I wonder how much you could reduce the entropy of this distribution if you knew something about the lexical heads of x1 and x0, or their general categories. And maybe you're going to get to that.
Great.
But
let's get through
another
it.
I mean, these are different semantics, so you might be able to guess if you knew what kinds of objects you were talking about.
So the general mechanism in the tree transducer to handle this would be the states. So this guy's going to have some sort of state associated with it, and this guy's going to. So if you do want to execute this translation rule, you might do it with both of these guys in the R state, and that will make sure that they sort of agree with each other.
One more question.
The other way of handling it is through the non-terminals. I mean, you can
Yep.
you can sort of go back and forth.
I don't
between
like
the
to
twos.
mess with the non-terminals. If it says MPP, that's what I mean. I mean, it's MPP, and maybe there's some states, but I get it. Yeah.
If you back up one slide, and maybe two, I don't know, where you were showing us, there you go. So in this tree, you are going to extract every subtree in some sense, right?
Mm-hmm.
Meaning, not even every subtree. Basically, if you think of this tree as a graph, every connected component of this graph is up for grabs.
Yeah, what it really does is identify as a subset of the English nodes that can be the root of some rule. So some of them can't be the root of a rule because there's a lot of crazy stuff going on with the alignments. So it might pick out a whole big section of stuff here and say that's my rule.
Okay, so I guess that's the part I haven't got completely. So if you think of the English words, and then if you just think of it as a graph with nodes and edges, and if you think of the Chinese words as other nodes connected further, so the tree just grows a little bit more. So what are the connected components that you're not allowed to extract?
Okay, so
Connected
every oval here has to have the property that no alignments can come in or out of it. So if this word part was aligned to that word over here, for example, then we wouldn't be allowed to, for example, extract a rule just right here. And so this wouldn't be the node of the root of some sort of rule. We have to go up and up and up and up until part and that Chinese word and this Chinese word are all in the same component, and that would send you all the way up to the S, and you get this giant nasty rule. So if the alignments are bad, then you extract very big nasty rules.
Sorry, and this is because you need you essentially need contiguity.
Because we trust the alignments, so we say those alignments are right, and there's no way to produce a rule if the alignment goes in and around. Just the rule wouldn't make any sense. You can't write it down as a tree transducer rule.
I mean, of course, the Chinese is the primary. We're going from English, from Chinese to English, right? So essentially, you try. Well, so one thing that's limited is what the Chinese phrases are, right? And that stays. And the question is how to react. I shouldn't say what the Chinese phrases are, but what the English translations of the Chinese phrases are. And so you will try a whole set of legal trees which will utilize the English translations.
You're in the future. You're maybe next year. So this year we think the tree is fixed. Its parts, our data objects that we learned from, bilingual data objects, are exactly like this.
I don't understand. How do you know the English tree?
Oh, we parse it with the parser that was trained on the, so it's noisy because the parser was trained on Wall Street Journal, and then we parse the bilingual text with the parser. So the word.
Oh, I know. I thought we were doing translation. I didn't think we're doing training.
Oh, this is training. Yeah.
Oh, this is
so
training. I see. I'm sorry.
Yeah.
Yeah. Okay.
So this is the training part. That's right. So the decoding is a different story. And even here we have I didn't say anything about the parameter estimation, which we also have to do. So these are all the rules from this training case, and there's a lot of other training cases. So each of these gets a count, and we have to smooth those counts. Yeah.
So if you're trying to move to less commonly taught languages, you might, you might not want to have a constituent parser. You might not have a constituent parser. Would this work if you had a dependency parser?
This particular algorithm wouldn't, but I think there are a bunch of groups exploring dependency grammar on both sides, in particular, or on the source side especially. So here we're using this on the target side. We can talk about that. So yeah, a lot of these things should work out. Okay. All right. Okay, so we saw these sample rules. Okay, so then with tree transducers, now it's kind of interesting to think about them, well, in general. So if we develop things for tree transducers, we could come back and apply that to machine translation, but maybe other problems. So a typical question you might ask, if the data is incomplete, can tree transducer probabilities be estimated by EM? So let's say we have a bunch of tree string pairs that are not aligned, let's say, or a bunch of tree pairs that were given in the data, and you have some rules. How can you automatically assign the probabilities to those rules, even though you don't know exactly which derivation or which rule sequence was applied to get from the input tree to the output tree in any given case? So there's a general algorithm to do this for tree transducers. Even the most complicated tree transducers, you can do this. So it's good. And this is derived from the great inside-outside algorithm, or I wouldn't say derived, but it's very similar. And MT, so this sat around for 3 years though before we could get any bang out of it. So it's nice to have an EM algorithm for the representation that you use, but it's really hard to get EM to do what you want. So now we have an algorithm that'll do, for example, take this tree and say, well, maybe that's not the right tree. Maybe if we binarize it, well, kind of hard to binarize this tree, but some of these trees have 4 children or 5 children, and so if you binarize those things, you can get better rules out. And so how do you binarize a tree? This way, that way, the other way? You can leave that up to EM, and it can discover that for you. So that's kind of good. And if you don't like those alignments, you can throw out the alignments and use EM to try to guess what the better alignments might be. So that's another thing you can do with EM. But I think there's lots more possibilities there. But EM often does the wrong thing, so you have to be careful with it. Another one is what algorithms are available for decoding with these tree transducers. So this is Fred's question. And I don't have any animation about that one, but we can talk about it if you have a question afterwards. So, and especially in machine translation, you have to mix in the language model. So if you mix in the in-ground language model into the decoding procedure, that's very nasty, and so you need special algorithms to be able to do that. How about tree transducers for language modeling? So this, if you went back to my noisy channel picture from before, there was a language model that generated English trees. It didn't generate English strings. So that's definitely more good future possibilities. You might just wonder in general for these things about determinization, minimization, all the stuff you worry about for finite state string machines, you can worry about for finite state tree machines. So we rediscovered this big world of tree automata theory that was started by Rounds and Thatcher and some people before working on tree acceptors. So these guys worked on tree acceptors and they worked on tree transducers. And we're actually motivated by natural language problems in this case. But very soon these things got disconnected. So the formal language theory went off this way and natural language went off that way, and didn't really come together very well, especially in tree automata. So tree automata basically moved to Europe and to Germany and France, and they've been doing work there ever since. Engelfried's thesis was a major landmark over there. And the Geksche and Steinby book is a very good book. Here's Magnus Steinby, very good guy. So he comes to visit us and gives us tutorials on tree automata, working with us on a project. Heiko Vogler at Dresden, probably Dresden is the biggest place for tree automata theory right now. So all these guys are much amazed that there's, for all these decades of work, that anybody would ever want to use tree automata for anything. So they're happy to meet us and happy to meet them, and it's kind of fun. So there's a lot going on there. There's workshops on tree automata. There's the textbooks. His textbook's out of print, and this textbook is by a bunch of French authors, and it's only online. It's not published. It's full of spelling errors. A really good book. Really good book. And then conferences. So we start going to these conferences to present what we've been working on in the more tree automata realm, even disconnected from MT. So let me try to talk a little bit about that. Well, any question about tree automata and what's going on there? Okay, I'll talk about it.
Is that Jim Thatcher? I
James
knew a Jim
Thatcher.
Thatcher at IBM.
James W. Thatcher?
Well,
Yeah, I think so.
I see. Okay.
So he developed the tree acceptors and transducers. So they thought of it as generalizing finite state string acceptors and transducers to the world of trees. And that it's been presented ever since as a generalization of finite state string machines. Because you could think of a string as a long, skinny tree. And so all the tree is just that kind of string, but there's some branching involved. Okay, so one of the things we've been trying to do on the side, outside of machine translation, is to develop a tree automata toolkit. So this has been worked on by Jonathan May, who's a grad student at ISI. So the first version was out last year, and you can play with it. It has some functionality, and it's inspired by the toolkits, the string transducer toolkits, ATT, FSM, and there's a bunch of them now. So the idea is you catch your problem in terms of tree acceptors and transducers, and your problem doesn't have to be MT. It could be music generation. A student did a project on music generation, tree automata last semester. It's pretty interesting. So anything you want, sentence compression, and all kinds of things. And if you can cast it that way and develop your knowledge sources in tree automata format, the grammars and the transducers, then you get a lot of implemented algorithms for free for reasoning or doing inference with those. And there's, in the world of strings, this has been going on, I think, profitably. So Pereira and Riley showed how to use string automata for ASR, and Kumar and Byrne have been using those things for translation. You guys have been using it for all kinds of problems. So this is a good thing that's been going on in the world of string translation, string automata. And for tree automata, there's a huge amount of literature to draw on, but also lots of open problems. So in tree automata itself, but also in how you pick a tree automata to match your natural language problem. So just to give you a feel for what's going on in terms of problems that people are solving. So you might ask, what's the in-best path through a lattice? So Viterbi had a nice algorithm for giving you the one-best path. And David Epstein at Irvine, down the road from us, had a very nice algorithm here. Very good asymptotic algorithm for giving the in-best string path through a lattice. And this is this algorithm is very good because you can have tens of thousands of nodes in your structure, and you can ask for millions of the top 1 million paths, and you get them all just like that. So it's much better than the naive algorithm you might implement. And often people use this year at a paper at HLT to work with very large in-best lists to produce very large in-best lists for machine translation. Okay, but that's all done in the world of strings. In the world of trees, instead of a lattice, you have a forest. So here's a packed forest full of an exponential number of trees, possibly even a loopy forest. So just like these, I shouldn't say lattice here, I should say finite state acceptor, which could have loops in it. So you can have a forest with an infinite number of trees in it, and you want the n-best out of that. And so Liang Huang and David Chang have developed a nice algorithm here. This algorithm doesn't have good asymptotic complexity, so it's good enough in practice. But this one is sort of provably has a nice feature, m log n. So there's still some theory room to play here, but in practical terms, this algorithm is really good. So probably best just to call it done and move on.
There was an earlier Spanish version of that algorithm, right? The one on the upper right. I don't remember if it's identical. I think it's very close.
Yeah, and I don't know if it's the same guys who also had an algorithm like Epstein. So they did agree. Yeah.
I think it is. Yeah, I'm blocking on the name.
I should put them in. So they also did a comparison between this asymptotically great algorithm versus their kind of more heuristic, lazy algorithm. And so in practice, it depends on what kind of graphs you have. That's the right. Okay, EM training. So if you have a tree transducer, if you have a string transducer, we know how to do EM. If you have a tree transducer, then it's a little bit more expensive. If you have a tree-to-tree, it's n-squared algorithm, just like that one. If it's a tree-to-string transducer, it's n to the fourth. And if it's I'll stop there. And determinization of weighted string acceptors, weighted tree acceptors, intersection, so you can intersect WFSAs. You can't intersect those context-free grammars because it's not guaranteed to give you a context-free grammar, but you can intercept the trees, the tree acceptors. And shoving strings through transducers gives you output that's WFSA. If you shove a tree through transducer, you get something called a weighted tree acceptor. And composition is another interesting thing. So a lot of what works in the string world is because you can take two transducers and build a single transducer automatically that does the job of both of them. And a lot of tree transducer classes aren't closed under composition. So the tree world is messier. So you can't necessarily take two tree transducers and make a single tree transducer that does the job. of both of them. So that's kind of active area. So I think the point of this graph, though, is that you would think that these problems have been solved a long time ago, but there's a lot of active work going on here, and only in the last couple of years do you find really good algorithms for all these things and a lot more. Any questions?
Yeah, this is actually a question about Tiburon, if I'm pronouncing that right. So if you, of course, you can encode all the string cases, right branching tree cases.
Yeah, you don't have to do that. You can just make a
Oh yeah, sure, right. That's
a
even easier.
long skinny tree.
That's if you're willing to have an infinite vocabulary of non-terminals, right? Or I'm sorry, if you're willing to have a large if you're willing to, if you don't make a distinction between terminals and non-terminal alphabets, I guess is what I want to say. And typically people don't, I know.
Yeah, okay, so it's like this W2 and so on, and usually put an end marker down at the bottom, and they say that's a tree.
Sure, right. Sometimes for reasons of implementation, people, when they're building trees, want to have a larger alphabet at the leaves, namely the whole vocabulary of Chinese or English, and only NP and BP and stuff with the enrollments. So yeah, so you can just encode it that way. In those cases, when you take the operations that Tiburon supports for that, how do they compare in efficiency to the AT&T toolkit?
Yeah, so asymptotically it's all the
all
the same. So running time, then that's a whole different story of the two different implementers and all this stuff. So this I would say is much slower. Tiburon is much slower than Carmel or AT&T toolkit. Not because it has to be, just because it is.
Yeah, that's the first version. I'm not trying to
That's right. So you're yeah. Okay. So I was going to drop.
Like if we wanted to use it for real work, or how slow would it be?
Very slow.
Okay.
Very slow. Yeah. So the first goal is to sort of get all this stuff implemented, and the second goal you go back and get it very efficient.
That's the right strategy.
Yeah. Familiar with that. Okay. So yeah, it's kind of funny to get used to strings like this, but if you wanted to have something like you're in state queue and you eat up W1 and you output Y1 and you go into state R, that's the usual string transducer thing here.
Yep.
So in a tree transducer, you'd say I'm in state Q, I have a tree rooted at W1, and its whole subtree under here, I'm going to call it X0. Well, the way you transduce this tree is put Y1 here and then go into state R and recursively process this subtree. So it's just have to get used to thinking of everything as a tree instead of a string. And then, so you can do all the string problems. I think this is part of the question. Can you do all the string problems first? And you can't. And this is the whole theory of generalizing the string transducers to make tree optimal.
Can you do composition in the cases where it works? For example, on these things?
Okay, so let's get into that. So this, just a few more slides on the types of tree transducers and walk through a little bit of the theory, just a little bit. So this is this is the type of tree transducer introduced by Rounds. It can do kind of funny things. You can have a tree transducer that can copy. So you can say, you know what, I'm going to make this left-hand side that's rooted at W1 has some subtree. I'm going to say the way you turn that into Chinese is make the root of the Chinese tree at Y1 and then copy this whole subtree, make two copies of it, and then process those maybe with the same state, maybe with different states. And it can do many things. It can look at the rest of so if you're used to string transducers, what if you didn't have to look at the rest of the string? You could just quit right there. Then you can do that too. You can delete whole subtrees without looking at them. So some of these things are copying, some of them can't copy, some of them can delete subtrees, some of them can't delete subtrees. And this is standard from the tree automata literature. Now, these are very restricted, so these guys can't even do things like Arabic to English translation, where the subject moves in between the verb and the object for kind of technical reasons. So you have to invent a whole other sort of parallel world where you can do these things. And you can prove things about these guys that are a little bit different from things you prove about these guys. So this was kind of where what you find in the tree automata literature doesn't actually match what you need to do for machine translation, say this Arabic English problem. So you have to build a little bit of a different automaton. And tree automata people go, yeah, you can do that, sure. And, makes sense. There's bottom-up transducers, or F frontier to root transducers. There's top-down ones, the R root to frontier. And they have different behaviors. So these are very similar types of machines. One that goes from the top down and one that goes from the bottom up. But this one can express things that he can't, and this one can express relations that he can't. So imagine a string transducer. You could build a left to right one and a right to left one. Imagine those were very incomparable devices. They're not. in the world of strings, but in the world of trees you get kind of funny behavior like that. And I guess this shows that, just to demonstrate, so the arrow means this thing is more powerful than that. This one could capture more tree relations than that one. So for machine translation, you'd like to go as high as you can, because you could capture all kinds of things. But you'd also like to go as low as you can to get good complexity. This one shows that if you take two top-down tree transducers and put them next to each other, that can do more than just any single one can do. So that's it's not closed-ended composition. And then there's a world here where we get down to stuff we actually use for machine translation. In here, these non-copying, non-delivering things, and whether they can have input epsilons or output epsilons really makes a huge amount of difference. Yep. So this is an unstudied or just now being studied area. How does this relate to string transducers and so on? Yeah. So one more graph here, one more baffling picture here. Did you like this one? Okay. So these are mentioned tree transducer classes that we've studied very carefully. Okay, and what you'd like to do for natural languages, you'd like to have something that's expressive. So it can rotate, solve this problem of Arabic to English translation. You want to do certain things with rotating trees around to capture what happens in human translation. So you want it to be expressive. And you also want it to be closed under composition, so we can do things like parallel search, all the groovy stuff you get from string transducers. And you'd also like it to generalize finite state transducer. So this is what Jason was bringing up. Anything I can do with the finite state transducer, I'd like to be able to do with the tree transducer. If it truly does generalize, like it's been sold by the Automata community for so many decades. So this is the picture so far. It's not exactly a great outcome. So the green ones are ones that are closed under composition, like including string machines here, this FS2, this is the familiar one that we know about. But the ones outside the green are not closed under composition. And that includes Bill Round's original transducer up here. So only some of them are closed under composition. And the blue one is whether they're expressive enough for natural language. I should say minimally expressive enough for natural language. So these guys are, these powerful ones are, but anything outside the blue, these are too weak to do even basic machine translation operations. And the pink one is whether it can do everything that the finite state string machines can do. And only these guys can. So there's a very active search now for new types of, so this one was just invented last year by the guys in Dresden working with us. This is the first one that can do, it's closed under composition and it's expressive for things like translation. But the search just goes on because you can see none of these many models that have been proposed in the literature can do all three of those things. So it's a good mystery challenge for the theory side. Any questions about that? Okay, so let me try to finish up. So here's what's been going on in our lab. So we've had, we started with machine translation research, got kind of stuck there, and then the tree automata research provided clean representations and fast algorithms to support that research. And then that research came back and said, well, these particular automata that have been proposed in the literature aren't quite what we need for translation. We need to modify them a bit. And then that brings back more research here about what are the properties of those modified transducers. So that's been a good going around there. And then there's the toolkit that I talked about, the Tibron toolkit. So again, the same research here gives these nice clean representations and fast algorithms that people can use for new applications, prototypes, student projects. And then we get user feedback that actually says, well, why can't I do this? So we currently, I don't know if this is in the latest version, it's on the web, but we warn people. If they try to compose two transducers, we warn them and say, these are not closed under composition, so by the rules of theory, I cannot guarantee you the answer I'm giving back to you is correct, but we give them back an answer.
Is the problem incorrectness rather than non-termination? I haven't tried working them through.
Yeah, it's incorrectness. So one of the open problems there is it a decidable problem to take two instances of an R transducer and decide whether there's an R transducer that's the composition of both of them. Yeah. That's maybe easier than this impossible one that says you can't do it. There's a lot of that, and the users here actually drive a lot of this. So. Okay, and then I guess just the level of effort. There's several people working on a DARPA project for machine translation, like you guys know about. Big project there. This is more or less Jonathan May working with me part-time. So he works full-time on this and me part-time. And then in Jonathan May's spare time, he builds this guy. So it would be good, I guess, to have a little bit more effort on this side rather than everything, virtually everything in the machine translation side. Because you never know what's going to come out of here. But good things have been coming out, and I think in the long term, or medium term, good things will continue to come out of there. Okay, so conclusion, making progress on machine translation, opening up the field of tree automata to natural language processing, and continuing this interdisciplinary research. So these three things were on my title slide, but there's also efficient algorithms, a lot of engineering, and grid computing, and all kinds of other stuff that you need to really make it work. Good. So that's it. Any questions?
Maybe one day here with the piece theory of autonomous nights that you have up there is that you may, certain data may be explained by one class of automata, but well, as you said, there's a trade-off between the expressiveness you might want to capture the data versus good runtime. And is it possible that thinking that you'll find one class of automata that will both explain the data and give you a good translation system is not the way to go? That rather you want to squash down the expressivity.
Yeah, I kind of like the what we settled on for machine translation. So it's going to enable a ton of follow-on work to work within that paradigm. As the translation.
What do you mean? What you settled? The one formula?
Yeah.
You settled
Oh,
on?
did I say what that was?
And on
No.
this slide is another criteria.
That's the one that we use for machine translation. Yeah. So it's which we liked because it's spelled excellent, but that was a total coincidence.
Right, L is linear, N is non-deleting, and T is top to bottom.
This is extended
Yeah. And-
left-hand side that you need for kind of this.
Right, and that allows you to do sort of like tree substitution grammar kinds of things, right?
Mm-hmm. Yeah, yeah. And then we have output epsilons, and we don't have input epsilon. But this thing does allow, it's very funny, the machine translation forest that we built. So here's the string coming in, and the decoder builds this forest. There are loops in it, which is very surprising to me. So you'll get a translation that says, please, 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 please do this, and then please, 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 even one more please, and one more. So you have to have those algorithms to be robust. Okay, so now I gotta get back to your question. Okay, right, are we satisfied with it? This will generate tons and tons of work for us. And eventually it will break down because there's some weaknesses to it. I mean, I could talk about one of the weaknesses, for example, and you can see what you think about it. These are backup slides. Okay, here we go. So, who does John think Mary believes I saw? You might want to translate that to John thinks Mary believes I saw who? In Chinese.
In Chinese.
Yeah. Okay, so if you were doing tree-to-tree transducers, and you start with the who up there, you translate this bit of stuff to John thinks, and then we process the rest of this in the Q who state. So this Q who state is going to just make a copy of this more or less.
Slash constituent.
And yeah, exactly. It's going to put the who down there. Here it goes. Here it goes. Q who VP with one child. That's the perfect place for the rule to fire to stick the
Right,
who.
the problem is if you change who to which pair of shoes, then you've got to send too much information through.
You got it.
Yeah.
So who's blue dog? I have. So if you want to send that down to there, then you're in trouble. But there's been this new invention from the Dresden guys where they have a. They can't go this way, but they can go that way. So if you work from down here, there's kind of multi-state. So it's not just a Q that they pass along, but they keep a Q1 and a Q2. Well, no, so they have so they can maintain a tree on the side, kind of in a little storage area in a different state as they walk up, and can stick it back in at the top. So there's, if you don't care about this problem because you're a really practical machine translation person, and this hardly ever comes up, don't worry about it. But I think eventually we get to problems like this that are.
Well, but I guess what I'm going to say is, why can't you do both? Why can't you say, well, I'm going to recognize this kind of stuff in my training data, and not learn the wrong thing in my impoverished transducer, but then I'm going to have a more clamped down transducer to actually produce output.
Oh yeah, that's a great. I mean, in general, if something can be solved with a string transducer, why invoke all this? Why not just use that guy? Now, whether a machine can look at some data and decide what's the most appropriate formalism for that data, that sounds a really hard problem. Great problem. Any other questions?
Well, for the sake of fun, I can give you one out of left field. So another bit of work that I could imagine barely might be useful, and the answer is probably that it's that you can't get it to work. It would be all the stuff about term rewriting systems, which are sort of like the transformational grammar version of this, because you get to take something that you've transformed and then transform it again. So it's like, you know, composing little local tree transducers with one another, more like it's sort of like transformation-based learning, where you do these rewrites. So as a historical note, the sort of the big revolution in phonology, it was Kaplan and Kay. In computational phonology, it was Kaplan and Kay who said, look, the rewrite rules that people write for phonology don't reapply to their own output. Another rule might apply to that output, but they don't apply to their own output. So they can sort of go through in one transducer pass, and that's what opened up finite state technology. So tree transducers have the same thing. And I wonder whether you might be able to get anything out of all this work that people in Europe have been doing on term rewriting systems.
Yeah. Oh, so that's a big question. So, you know, Bill Rounds invented these things for transformational grammar. That was his motivation. Because Chomsky was so messy. Those transformations in Chomsky's book, like he has trees and then he transforms them into strings, but then they need to be trees for the next transduction rule to end. So he's trying to clean that up. So I think composition is a big problem here. So just chaining these things together is already a big problem. Just say not that I'm more complicated. Things like term rewriting can do that. So I think we're trying to focus on how to chain these things together so that, for example, even for translation, you might want to have something that takes an English tree, restructures the English tree, does something else to the English tree, and then translates it into Chinese. And I stick my Chinese back, and it goes back through that cascade. So that's already hard enough. So I'll see I don't know if I can say anything enlightening about the term rewriting now. But those things that don't have very good computational properties either.
Let me ask you another question, which you probably implied but didn't say explicitly anything about, which is you're talking about expressiveness for NLP, right?
Yeah.
But you're now thinking about, does it cover the real translation pairs I see in some corpus X, or can someone by introspection come up with a translation pair which this doesn't cover, and so on? You haven't said anything about parameterization, so like, you know, so at the cost of covering more NLP is obviously more parameters and more detailed structures. So at what point does the trade-off start to be like not worthwhile?
Well, I don't know if that's right, because you know, all these guys are very, very similar. So there's slight variations from our point of view, and they all have the same number of rules and they have the same number of parameters. So it's not necessarily the case that things in blue are more complicated than things outside of blue. You just have to have the right kind of device to do the job.
And is the parameterization obvious? I mean,
no, super unobvious. So you got one more good figure out here.
Okay.
So if you have something like S, MP, VP, X0, okay, so this could apply, or X0, VP, V. Let's say either one of these rules could apply to your input tree.
You're right.
So shouldn't they compete? So if you're doing conditional probability given the tree and you want to do something to it, these rules should compete on that tree. But there's some trees where these don't compete, namely the ones that don't have this WC. So you can't just build your conditional probabilities offline like you always do for string transducers, because you have to wait till you actually get the tree until you can find out which rules compete with each other. So it's super nasty problem. Okay, well I think